Welcome to our second set of fluid mechanics practice questions. In this video, we will dive into fluid statics. Ensure you are referencing the FE handbook while answering these questions. As a supplement to this course, check out the full-length practice exams and other topic-specific practice questions that can be accessed through the link in the description. Now, let's get started with some fluid mechanics practice questions. Practice question 1. A 1.2 meter wide rectangular gate is submerged vertically in water and is inclined at an angle of 45 degrees from the horizontal. The gate is 2 meters long, and its top edge is located 0.5 meters below the water surface. Determine the slant distance from the water surface to the center of pressure, YCP, along the inclined plane. The center of pressure is the point where the total hydrostatic force can be considered to act. For a submerged surface, the slant distance to the center of pressure is found from three main components: the slant depth to the centroid, the moment of inertia of the gate about the centroidal axis, and the area of the gate. Next, we compute the geometric properties of the gate. The gate width is given as 1.2 meters, and its vertical length is 2 meters. Since the gate is inclined at 45 degrees and the top is submerged 0.5 meters below the water surface, the slant depth to the centroid is calculated by adding half the gate length to the top edge depth, giving us a slant depth of 1.5 meters. We then calculate the surface area of the gate by multiplying the width by the height, yielding 2.4 square meters. For the moment of inertia about the centroidal horizontal axis, we use the standard formula for a rectangle and compute it to be 0.8 meters to the fourth power. Finally, we substitute all of these values into the center of pressure equation. This gives us a final slant distance from the surface to the center of pressure of approximately 1.722 meters. When rounded to match the options provided, we get 1.71 meters, which matches answer choice D. Practice question 2. A tank is connected to a U-tube manometer containing two immiscible fluids. Fluid 1, with density 850 kilograms per cubic meter, fills the left leg, and fluid 2, with density 13,600 kilograms per cubic meter, Mercury, fills the right leg. The vertical distance between the fluid levels is 0.18 meters, and the pressure at the top right opening is atmospheric. What is the gauge pressure P0 at the tank connection point? The left leg of the manometer is filled with a lighter fluid, and the right leg contains mercury, which is significantly denser. The key information provided includes the densities of both fluids, the vertical height difference between the two fluid columns, and the fact that the top of the right leg is open to atmospheric pressure. Since we're looking for gauge pressure, that is, pressure relative to atmospheric, we can ignore the atmospheric term and focus on the pressure difference caused by the two fluids. The pressure at the tank can be found by taking the difference in pressure between the mercury column and the lighter fluid column. That difference depends on the difference in fluid densities, the gravitational constant, and the vertical distance between the fluid levels. Substituting the given values, we get a difference in densities of 13,600 minus 850, which equals 12,750 kilograms per cubic meter. Multiplying this by gravity and the height gives us approximately 22,926.79 pascals. Rounding to the nearest whole number, the gauge pressure at the tank connection point is 22,927 pascals, which matches answer option A. Practice question 3. A mercury barometer is used to measure the local atmospheric pressure. The height of the mercury column in the barometer is observed to be 0.760 meters, and the specific weight of mercury is 133,322 newtons per cubic meter. Assume the vapor pressure at the top of the column is negligible. What is the atmospheric pressure in pascals? To determine the atmospheric pressure using the mercury barometer, we rely on the fundamental principle that the pressure at the base of the mercury column equals the atmospheric pressure, provided that the top of the column is exposed to a vacuum and the vapor pressure is negligible. This allows us to simplify the barometer equation to state that atmospheric pressure is equal to the specific weight of the fluid multiplied by the height of the column. Next, we substitute the given values into the equation. This gives us a pressure of approximately 101,325 pascals. This result matches option B. Practice question 4. A vertical rectangular gate is located on the side of a water tank. The gate is 2.5 meters wide and 3 meters tall. It is hinged along its top edge, and the top of the gate is flush with the bottom of the tank. The tank is filled with water to the top of the gate. What is the total hydrostatic force acting on the gate? Use the specific weight of water as 9,810 newtons per cubic meter. We begin with a general formula for the force on a plane surface submerged in a fluid. This equation tells us that the force equals the product of the specific weight of the fluid, the depth to the centroid of the surface, and the area of the surface. The specific weight is given in the problem, and the depth to the centroid can be found since the gate is vertically placed and its top edge is flush with the water surface. Next, we plug in the known values. The gate has a width of 2.5 meters and a height of 3 meters, so the area is 7.5 square meters. Since the gate is vertical and the top edge is at the surface, the centroid will be located at half the height of the gate, or 1.5 meters below the water surface. The specific weight of water is given as 9,810 newtons per cubic meter. Now, we compute the force using the values. Rounding to the nearest whole number, we find that the total hydrostatic force on the gate is approximately 110,362 newtons. Therefore, option C is the correct choice. Practice question 5. A 1.5 m wide rectangular gate is submerged in water and inclined at an angle of 60 degrees from the horizontal. The gate is 2 meters long, and its top edge is located 1 meter below the water surface. Calculate the total hydrostatic force acting on the gate. We start by identifying the correct equation for the hydrostatic force on an inclined surface. The force can be found by multiplying the specific weight of the fluid, the area of the surface, the slant depth to the centroid, and the sine of the angle of inclination. This formulation accounts for the vertical depth of the centroid relative to the fluid surface through the sine term. Next, we compute the necessary geometric quantities. The gate is 1.5 meters wide and 2 meters long, giving it an area of 3 square meters. The slant distance to the centroid is calculated by taking the top edge depth and adding half the gate's length multiplied by the sine of the angle. Since the top of the gate is 1 meter below the surface and the gate is inclined at 60 degrees, we find the centroid depth to be approximately 1.866 meters. Now that we have the specific weight, area, slant depth to centroid, and sine of the angle, we substitute these values into the force equation. This results in approximately 50,910 newtons. Therefore, answer choice C is correct. Practice question 6. A horizontal cylindrical tank is partially filled with a liquid of specific weight 9,000 newtons per cubic meter. A rectangular inspection hatch 1.5 meters high and 1 meter wide is located on the vertical side of the tank. The top edge of the hatch is located 2 meters below the liquid surface. A manometer connected at the centroid of the hatch shows a differential mercury height of 0.4 meters. Atmospheric pressure is 101,325 pascals, and the specific weight of mercury is 133,100 newtons per cubic meter. What is the distance from the liquid surface to the center of pressure on the hatch? We begin by locating the depth of the hatch's centroid. The centroid of a rectangular shape is at its midpoint, so since the hatch is 1.5 meters high and its top is 2 meters below the liquid surface, the centroid lies 2.75 meters below the surface. Next, we determine the pressure acting at that centroidal location using the manometer reading. The manometer shows a differential mercury height of 0.4 meters. Using the specific weight of Mercury, we find that the pressure at the centroid is 53,240 pascals. With that pressure, we move on to find the geometric properties of the hatch. The area is straightforward. Multiplying the height and width gives us 1.5 square meters. We also need the second moment of area, or moment of inertia, about the horizontal centroidal axis. For a vertical rectangle, this is 1/12 the width times the height cubed. Plugging in the values gives a moment of inertia of 0.28125 cubic meters. Now we apply the formula for the center of pressure, which adds a correction term to the centroid depth. This term is the moment of inertia divided by the product of the centroid depth and the area. Substituting the known values, we get roughly 2.82 meters. This matches answer option B. That concludes our practice questions for this unit in fluid mechanics. In the next lecture, we will continue with fluid mechanics and cover topics under fluid dynamics. Again, if you want more example questions or complete FE practice tests, visit the link in the description or on screen. Thanks for watching.